We've all heard of zero-knowledge proofs. If you've been listening to us, you definitely have heard of zero-knowledge proofs. But in short, they allow you to prove that you have some information without revealing anything about this information itself. This is the privacy aspect, which is crucial, and it has great implications in the industry in privacy-preserving technologies like privacy coins, shielded addresses, privacy pools, private voting. But there are more properties from ZKPs that are not necessarily enhancing the privacy of blockchains, but they can be used for scalability. For example, ZKPs have the properties of succinctness and work saving. Succinctness means that the size of the proof is smaller than the data you are proving that you know. And work saving, well, as you can imagine, it means that it's faster for the verifier to verify a proof than to analyze the original data itself. So this is the basis of what are called ZK-Rollups, zero-knowledge rollups, where you just prove that a state transition is valid, state transition being transactions or smart contract calls and different operations, and you post that proof on chain in a way that it occupies less space than the original operation, succinctness, and it is faster to verify, work saving, boom, scalability. Okay, I felt I needed to prepare you with some basic knowledge because in today's hot seat, we are going on a wild ride with one of the pioneers of ZK-Rollups, Jordi Baylina from Polygon zkEVM. He has also created many libraries and tools for working with ZKPs that they are integrated in other projects. In this episode, we will freestyle a bit and we'll jump between the deep technical parts of the ZK-VM to the implications for the future of scalability and Ethereum.
Thank you very much, Paul. It's a pleasure. It's a pleasure to be here. Well, the zkEVM, I mean, probably is one of the hottest topics currently in the space. As you know, everything is about scaling Ethereum in the case of the zkEVM, scaling blockchains in general. What's the main idea? The main idea is of scaling is when we launched Bitcoin in 2009 was really nice, and it was very. I mean, it was I would say a historic event. I mean, it's just humanities from that day. We know how to transfer value through internet, so I think it's an important achievement. But it has a big problem. The problem is that all Bitcoin can do 1,000 transactions every 10 minutes. I mean, this is fine if there is, 100 friends using it. But if you want this to be really a scalable, I mean, just worldwide, where everybody have access to this and everybody is using it, and a mainstream system, as you can imagine, 1,000 transactions every 10 minutes, it doesn't work. I mean, you can do whatever you want, but at the end, this is the limit in there. And why it doesn't work? Okay? To understand why it doesn't work, you need to go to the consensus. Reaching consensus is slow. Consensus in algorithms is very clear. It's not that clear, but consensus, for example, between persons is we understand why. Imagine that you want to get a consensus where you want to go to dinner tonight, and in reaching a consensus, it's a process. I mean, somebody needs to process, maybe to suggest something. The others may agree or disagree, and maybe you set up a voting, and maybe there's this voting. It says no, and maybe somebody else proposes, but at the end you reach a consensus. Okay, but in protocol algorithms, this consensus algorithms more or less do the same, or at least something similar. So, but at the end, all the participants on the consensus, they reach a point that says, okay, this is the right state. Okay, and this state is so in the case of a Bitcoin, is reaching the right state means reaching a state where, deciding which transactions are processed. We go from one state, so we have one state, we process some transactions. We need to reach to a consensus to which transactions we process, and when we reach a consensus, then we go to the next state, and this is blockchain. Okay, but reaching this consensus is slow. Okay, it's slow for many reasons, but the biggest reason, because when you are communicating, is first that everybody needs to know these transactions, and everybody needs to process those transactions, needs to validate those transactions. We cannot reach a consensus saying that one transaction, there is one fake transaction that sends $10 million to my account from nowhere. I mean, this is not a valid transaction if we want to have a fair system. Okay, so everybody in the consensus needs to check all these transactions, check that they have enough balance, check that the signature is correct, and then they accept the consensus if these transactions are valid. So everybody needs to process these transactions. If we have 1,000 transactions, processing 1,000 transactions is not that much. But if you want to process 1 million transactions, then this is a long process. And to reach the consensus at the end, the problem is the one that goes slower. Okay, so we cannot go faster than the slowest computer in the network. Okay, and so okay, what we have, because I mean, processing transactions, it takes a while. You need to, I mean, you need to read the database of all the accounts. You need to validate the signatures, and this is, I mean, if you are validating that in a Raspberry Pi computer, it just goes to some rate, okay, and you cannot go much more than that. Actually, Ethereum, for example, can do it a little bit better. It can do about 30 transactions per second, which is much better. But at the end, is the same. It has the same problem. It's the same problem is that everybody needs to execute those transactions. So solutions for that, well, for a while we were like thinking in the space. A lot of people were thinking in different approaches. Here is where things like state channels, payment channels, lightning network happen. At some point, somebody invented one thing called plasma, which I would say was like the beginning. It was the father of rollups. I mean, it was like the first idea of a new chain that scaled somehow. But then came the rollups. And what's the trick of the rollups? Okay, the trick of the rollups is at the end is splitting. So first is splitting the data availability and the process. Okay, and in order to understand that, we need to understand how the idea of the zero knowledge proof, how they work, or more, or even better, how the validation proof work, which is the same with different name. Okay, validation proofs is a technology, it's a new technology, it's a very recent technology that allows you to compute any program. Imagine that you have a program, and verify the idea is that allows you to verify, anybody can verify a program without having to run the program. Let me put you an example. Imagine that I have a program that takes 1 week and it does a very complex operation. For example, validating 1,000 transactions. Okay, so if I give you the result, so this goes to a state, I process this transaction, and the result is okay. But if you want to verify this execution, I tell you the result of these transactions, I give you you have the transactions, but the result of these transactions are valid. What you have to do in order to validate that? Well, the naive way is you just execute again this program. Okay? This is the best way to validate an execution is executing it again. Okay, but with this validity proof, the idea is that I can execute the program, but together with execution of the program, I can generate a proof of the computation, so that you, in the other side, you don't need to run you don't need to execute the program again. You just get the result and validate the result with this validation proof. Okay, and the cool thing here is that with this technology, you can have so that the program can be very, very, very long. Can be a program that takes 1 day, can take 1 week, 1 month, 1 year. Okay, but the validation of this proof is time constant. It's very few milliseconds, no matter how long this program is. Okay, and this technology that's relatively new is the key of the rollups. So the idea of the rollups is that from now on, ZK-Rollups, we are talking from now on, the people, so the nodes in the consensus, they don't need to execute the transactions. they just validate this. They just validate this proof. So because they don't need to execute the transactions, they just need to validate this proof. Theoretically, you can process as many transactions as you want. Of course, somebody has to process them, and somebody needs to generate this proof, which is not cheap. Okay, but you can have, I mean, this proof processing thousands. Just nobody. I mean, the consensus just the people just validate this proof. Okay, so
Jordi,
ZK-Rollup. Yeah, sorry.
no, no, no. Just I was about to say two things. Number one, we have a very technical public, so don't be afraid of getting deep into the weeds. And secondly, and I guess that's where you were going right now. But secondly, it's like, okay, this sounds like magical, right? Like we can validate that this is true without actually having to run the computation. But I think it's not that easy. I think what is the previous work that we have to do so this becomes possible? And I think this is the construction to the zkEVM, right?
Yeah, well, the idea here is that doing this process, so generating this proof, which is the key of the zkEVM, I mean, it's not easy. Okay, so you need to actually, it's like the way to think about this. You need to put the idea is you need to create a kind of a relationship between the inputs and the outputs. Is like a mathematical formula, so with mathematical constraints from the input and the output, and this is, I mean, you need to convert a program to this mathematical constraint. Okay, this is the kind of the arithmetization altogether. Okay, so this is how you write ZK circuits or statements for zero knowledge. Okay, and this at the beginning was at the beginning of this, it was done very by hand. I mean, for example, if the people here have been using this kind of programs, okay, and then the idea is that you mainly when you define a constraint, so you define a witness, okay, which is a set of values, and then you define constraints, which is relationships that these values needs to hold, okay, and then okay, but these circuits are with values, okay, operations. I mean, its constraints needs to follow. So as more constraints has a system, as more complex. Okay, and the problem is that if you want to build a zkEVM, the number of constraints that you need to implement is billions, if not trillions. So it's like a huge number. Okay, and processing technically is possible, but processing that's the difficulty here. Okay, so here the biggest technology, so the biggest breakthrough. There is a couple of breakthrough technologies that happen from Circon for the zkEVM. Okay, the first is the polynomial commitments. Okay, polynomial commitments is instead of these relationships, instead of relationships between values. Okay, and then you have, I mean, you have three values, and then you say that the value A plus the value B must be the value C. Okay, this is a constraint. So instead of working with values, the idea is that we can work with polynomials. Polynomials, a way to understand a polynomial is like an array of values. So a polynomial, you just take the evaluations to some specific points, and imagine a polynomial of degree 10. The evaluation of degree 10. I mean, you have with 11 points, you can represent with 11 evaluations, you can represent a polynomial of degree 10. Okay, so you can understand polynomials as an array of values. And the idea is that when we have a constraint, a polynomial constraint, so a polynomial A plus polynomial B must be equal to polynomial C. This is a polynomial constraint. Actually, we can do like 11. If the polynomial is of degree 11, then that means that we can do 12 constraints at a time. If this polynomial is 2 to the 23, then a single relationship, we can do 2 to the 23 constraints at a time. Okay, and this technology of polynomial commitments allows us to do a lot of constraints the same, because it's our polynomials, so a kind of a processor. So allows us to do a lot of polynomials at the same time. Okay, this is the breakthrough. So the way of designing circuits today is these high polynomial commitments, and this allows us to, I mean, to increase like 6 orders of magnitude of what you could do in what you could do in
Ethereum.
Yeah, no, in Circom and in the previous circuits. Okay. This is
Okay.
the one of the biggest revolution. And then in the zkEVM, mainly what we built is, well, first we built a language. It's called PIL, Polynomial Identity Language, in order to generate and to create these polynomial identities. PIL means Polynomial Identity Language. Okay, this create this arithmetization. Okay, so for your information, for example, the zkEVM is less than 1,000 lines of code of PIL. So it's not a big, it's not a big thing. Okay, when it's huge, but this is not a big thing in this language. This is the arithmetization, and this arithmetization mainly what it is a kind of a processor. With this arithmetization, we build a processor, so state machines of a processor. Okay, and on top of this processor, there is on top of this processor there is well, it's an assembly. So this processor can execute a program, can execute a ROM. We can encode this ROM, and then this ROM is like part of the proof. Okay, and then so we have a processor that's executing this ROM, and this ROM, what it's doing mainly is emulating Ethereum. It's emulating the EVM. So it implements all the opcodes, implements the signature verification, implements pairings in the case of the precompiled smart contracts, implements everything like Geth is doing. I mean, it's like a client, but it's running in assembly, in a special assembly with this processor, this algebraic processor that's built inside the zkEVM. This is probably one of the biggest revolutions, so one of the biggest breakthroughs for the zkEVM. And the other one is the recursion. Okay, the other interesting thing about the zkEVM is about recursion. In the zkEVM, we are using recursion mainly for two reasons. Okay, one is to reduce the size of the proof. So the recursion at the end is generating a proof that proves another proof. So it's a proof of a proof. This is a recursion thing. Okay, so doing a proof of a proof, the idea is that the second proof is smaller. Okay, or even a different type. For example, in the last step of the recursion, we are converting a Stark to a Snark. Stark is a big proof. It's a big that we have verifies this Stark where this is encoded with Flonk, which is a variant of Flonk, and then this for packing. I mean, for doing a Stark of a Stark, for doing this Stark smaller, and the last part for converting to you can take. Okay, and then with this you can build like kind of a tree of proofs. So it's like kind of at the end you have a proof that in our case for 25 and 26, and you can create a proof that proves both of them. Then you generate a proof of the block 27 and 28 and generate another proof. And then you take these two proofs and generate a proof of a segment that goes from 24 to 28. So that generate the full segment. And with this, I mean, we have generated, for example, aggregations of more than 4,000 blocks, okay, which is its proof is already a big one. Okay, and it's so this recursion, and with the Starks, this is very easy because we are doing full recursion. Starks don't require cycling elliptic. I mean, cyclic curves for doing this recursion. They don't Starks are not based on elliptic curves. And you can just creating a Stark from another Stark is very straightforward. And so this allows us to have full recursion. And the Starks also, we are using Starks with a small prime field that allows us to generate these Starks really fast. Actually, for example, generating a proof for a zkEVM of about 10 million gas, it takes about less than 2 minutes altogether in a big server, but let's say in a normal server, so in a server 128 cores with half terabyte memory. It's a big server, but something that you can buy in a store. I mean, it's something that it's like a normal servers there. Okay, so that's a little bit the breakthroughs, and this is the biggest discoveries or the biggest things that we bring to the space for the zkEVM.
Wow. Okay, fantastic. That was heavy. I have a lot of questions, but I think our audience will be able to ask a lot more questions. and a lot more accurate. So, have we got any questions yet from the public? Feel free to raise your hand to be able to speak or type for your question. Okay, so in the meanwhile, I have a question. The way you think about it, the way you talk about it, just creating the language, specifying the ROM, creating this algebra, it almost seems like you come to think of the zkEVM not as a programming challenge. You almost look at it from a systems perspective. Do you think so? Do you think your background as a telecommunications engineer sort of like gave you a different perspective than just coding and than just like dropping and creating something? And what is the advantage and disadvantage that you might have brought that the systems approach has over other approaches?
Well, definitely yes. My background is in communication engineering, but I've been doing hardware, for example, for a long time in my life. I've been doing all levels of hardware. I mean, from programming FPGAs to doing boards, programming the firmware, the hardware. So my hardware, I mean, I understand all the layers. I mean, sometimes I say myself that I'm a specialist in many things, but actually I'm a better specialist of everything. So I'm a more generalistic guy. But in this case, it allows me just to connect all the pieces. I mean, because here you need to connect pieces from the math and from the crypto. You need to connect ideas from the hardware design. You need to connect pieces from the assembly and, let's say, firmware design. You need to connect pieces of Ethereum as a system, the EVM, the zkEVM. So actually, it has been like, for me, this project, sometimes I say this is the project of my life for many reasons. But one of the reasons is because this project allows me to connect a lot of the fields that I've been like working in my life and putting them all together and having a good understanding of how this engineering by divide and conquer, or the engineering by layers work. And this, for me, that this is something that, for me, the way that we design this, for me, is something that's very natural, the way of thinking this way. But it was not trivial at the beginning. And I tell you that when you have to convince investors and business people to say, no, I'm going to create a full stack, I mean, from the beginning to the end, it's not easy, because it's like, I mean, you want to do like many things, but at the end, this has been the I would say the biggest differentiation and the biggest the right thing to do. And well, we're seeing right now, I mean, many other projects, they are following our paths in this sense. This gave us a lot of advantages. This layering things, this allows us to work in parallel, to have specialized teams to work in each. I mean, somebody was doing the arithmetization, the other was doing the compiler, the other was doing the prover, the other was doing the ROM, the other was doing the testing. I mean, with this allows us to split the team in different teams, specialized teams for different things. Even for the auditing, for example, we can also divide the auditing effort. I mean, there are some auditors that are very mathematical. The ones that are auditing the more the cryptographic part, maybe they don't need to understand something about Rust or something about assembly. The others are specialized in assembly, or people that's specialized in the EVM. Maybe the people that's specialized in the EVM, they don't need to know a lot about the arithmetization. Or the people that knows about, and that's his mindset of the arithmetization, they can focus on that. So this allows us, for example, to have different teams with different skills sets also work in parallel and check on that. And this is why we actually, at the end, we did the work. So a work that was expected to do in maybe 4 or 5 years, we were able to do it in a couple of years because of this architecture design.
Definitely, that was very fast. Since we first heard about the zero knowledge EVM, that has advanced a lot. I'm going to read a question from the public, from Pau. Are there any plans to include a privacy layer to the Polygon zkEVM, something such as new opcodes that would allow sending private transactions or interacting anonymously with smart contracts?
We already implemented the pairing precompiled to smart contracts. They are going to be available in forkid6. We are deploying forkid5 right now, but it's going to be forkid6. Let's see if this can be by the end of September, beginning of October. But all the code is there. I mean, you can check it in the repos.
What is forkd6 and forkd5?
Forkid is it's like the forks, the naming of the fork. Instead of putting a name of a city like Ethereum does, we are just putting a name, just putting a number there. So
Right.
we started with forkid4. Actually, this is because we did some forks during the testnet. So we start, the first one is forkid4, which is a way of starting the things by the right number. And we are now doing the first big update of the EVM. This is the forkid5 that we are still testing and preparing and including all the things, but let's see if we can do it in the upcoming very soon. I'm not saying more next week because it always happens something on that, but very soon. This is we are testing it right now very hard. And the next is forkd6, which is already implemented, and it's just a matter of auditing, testing, auditing. The problem of these forks, I mean, you need to re-audit everything, and you need to go ahead, and it's a little bit slow, the process for putting in production all these things. But they are ready, and yeah. So this, in the case of this, and then this is pairings. With these pairings, you can create a zero knowledge. So you could run, for example, a full Tornado Cache on top of that, or any voting system, or any smart contract that uses this precompiled to smart contract.
Mm-hmm. We have another question from Think Decade, which I have just invited to join. Perfect. You're right here. Feel free.
Hey, GM. Awesome and very insightful conversation so far. Thank you very much. And so I've got a couple of questions. I don't know whether I should hit you with all of the questions or one at a time. Choose.
Let's start with one, and then we can do the second one.
Okay, cool. Yeah, so I think that the conversation has been very technical so far. What I'm very interested in is what are some of the biggest potential benefits of ZKPs in the real world beyond crypto? That's my first question.
Interesting piece of ZK beyond crypto. I mean, ZK is a part of crypto. I mean, it's a cryptographic primitive itself, okay? But besides the scaling blockchains, let's say, of course, we have the privacy, all the privacy applications. Here we have a voting system, we have identity systems. I mean, everything, private payments, so everything related to privacy. This is important, but it's also. I would say that the ZK, the most important part is it will play a huge role in humanity because it solves one important thing that the humans we are fighting with, and currently, for example, the every time that this privacy, I mean, we have this balance between privacy and security in governments. They are saying, no, everything needs to be, it cannot be private because we need to avoid terrorism, and then we need to check that everything is fine. Or but I mean, but who controls this data, and who knows where this data goes? And maybe this can be even more dangerous for that. And in the other side, we have the right of privacy. I mean, I think this is a human right, being able to communicate with somebody else, or having your secrets. I think that's something that everybody should be able to have. It's a value for itself. And these things, I mean, you can have one thing or the other. It's a kind of a balance, at least until now. The zero knowledge allows you to reveal or prove just the information that you want. Okay, so it's like, imagine that you have a private information. You do a query. Maybe you are interested. Maybe, for example, if you can apply to an insurance, if you can apply to an insurance. Okay, this is a yes/no information. It's like, according to my, medical records, you can apply to this insurance or you cannot apply to this insurance. But right now, I have, if I want to prove that I can apply to this insurance, I probably need to give to the insurance company all my all my medical records in there. With a zero knowledge proof, I could hold my medical records signed by the doctors and signed, so that is real medical doctors, and I could generate a proof that I can apply to this insurance without having to give you the full, the track record, right? Just a yes/no answer. It's a query on my data, on my private data. It's a query, it's a proof that this is correct, okay? But you don't need anything else, okay? And this can be done with this zero knowledge. It allows you to do things and proving just the minimal that you need in order for these things to happen. So this solves this dilemma between privacy and security. This allows you to have both without having to give away any of both. Okay, so that's why one of the reasons why this technology is very, 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 very important in these privacy things. But there is a lot of applications. There are some, we can put you some strange cases, but give you an example. For example, a fishing boat that wants to reveal that he's fishing in the right, in a valid zone, but they don't want to reveal the exact place where they want to this fishing. Okay? You can do that with zero knowledge. Or, for example, for fake news. So right now, for example, there are projects that the idea is you get a camera, and the camera do a picture together with a GPS, okay, and then you can prove that the picture is done with a camera in a given place. But this, for example, okay, but maybe that this image has been processed maybe with some filters or maybe crapped, but you can prove that this image comes from there, or maybe there is some aquas, some backgrounds, but it allows you to prove that this image has not been manipulated or has been manipulated with very specific filters in there. So this allows you to prove that, for example, a picture was taken in a given country, in a given position, and so on. So this allows you to reveal just the right information, to prove the right information without having to reveal all the information there. Okay, and this technology is very useful for this, among many other things. But this is things. For example, a lot of other applications. For example, in AI, for example, that's like applications that can prove that this is a result of a given AI algorithm, but without revealing the AI algorithm itself. Okay, or some of the parameters of the AI algorithm, or without you having to run this algorithm, or a training. Okay, so it's like sometimes I can give you the result of a training, but without you having to prove that you did that. Okay, so this proving information. This is a lot of applications that can be done on that, and of course, scaling blockchains is probably the trigger one, the one that made this technology to improve so much in the last years.
Exciting developments. We have Fisher as well in the public with another question.
Hello. Yeah. So I was wondering if I understand things correctly, and please stop me if I say something wrong. Yeah, so basically we have Ethereum, which is like the Genesis, quote unquote, smart contract blockchain. And now we have, yeah, you have developed the zkEVM, which, yes, it's just a part of it. It's what computes things, to put it some way. So my question would be, it's yeah, in your plans for the long term, like you have now this execution layer, and now Ethereum it has moved to consensus layer, like dividing those two clients. Yeah, in your, like, in the future, in your end goal would be to eventually yeah, like be the main EVM there, so because yes, you can basically prove long chunk of information easily. So yeah, yeah, my question would be that if at the end you would like to, yeah, still relying on Ethereum, of course, mainnet, for data availability and stuff, but yeah, like being the main EVM out there. Yeah, if that makes sense.
I'm not sure about the question, but let me answer a little bit things about Ethereum. So the strategy of Ethereum, the strategy of Ethereum, scaling Ethereum, was to split these two problems. So one problem in two problems. One is the data availability problem, and the other is the execution layer, or the proof of execution. And that the rollups, they solve this execution problem. As I said before, right now you can generate a proof that with a few milliseconds you can prove whatever you want, and this scales forever. Of course, you need forever. I mean, you need the hardware to build that, but actually parallelizing hardware, you can process as many transactions as you want. Okay. The other condition for this to work is the data availability. What means data availability? Data availability means data is available. Means that anybody at any time is able to have access to the transactions that are included in the rollup. There is an attack here that's one of these operators or sequencers includes one of the transaction. That's a valid transaction. You include it in the on rollup. You publish the state root. I mean, you publish this hash of this hash of the new state. There's a new state that's valid. You prove that's valid. But if you don't know this state where it comes from, so if you don't know this transaction because this transaction is hidden by the sequencer, then the rollup would just stop and your funds would be locked there forever. Okay, so and that's why it's important that so you don't need to execute the data, but the data needs to be available. Okay, and this is mainly what Ethereum, the layer 1 of Ethereum is doing. Okay, the cool thing of that is that you can do that with easily with sharding, because at the end, data availability. So blockchain is very good for data availability, because I mean, if a data is on chain, the data is available. The problem is that the quantity of data that you can put on chain is limited. Okay, I mean, you need to get consensus, but you can have many blockchains. I mean, and then you can scale having many blockchains. This is what it's called shard. And so if you have many blockchains, you can have as many data as you want. Okay, so this is the first step, is being sure that this data is available, that anybody can recover this data on that. And the second is the zkEVM, the data, the processing this data. Somebody needs to take this data and process this data, take this data as transactions and process this data. Okay, so Ethereum is working in the mainly data availability. In the next hard fork, or very probably by the end of the year, beginning of next year, it's going to be enabled this proto-tank sharding. Proto-tank sharding is like the first step for this sharding. This will multiply more or less by 10 the capacity of Ethereum in data terms, also in data availability terms. And this is just the first step. The next step will be sharding and full sharding, and then full sharding will multiply all this availability by number of shards, which can be, I don't know, 60 or as many as you want. Okay, so the strategy is there. Then and here from the rollups perspective, I expect that in the short run, it's going to be like many rollups. Actually, I expect there's going to be many constellations of rollups. So in Polygon, we are going to have like the Polygon 2.0 is mainly a constellation of rollups where you can link public and private rollups with different sequencers. I mean, maybe centralized, decentralized sequencers with different data availability rules, but they will share the liquidity, and then they will you will have a composability between rollups really fast, so you will be able to talk from one rollup to the other, just like transferring, so that you see it every much as a single network. Okay, and this is governed at the end is that all these rollups will share the same prover. Okay, and this is what allows you, sharing the same prover allows you to share the same liquidity pool, and that is what gives the security to the full system. Okay, but this is what we call a constellation of rollups. Okay, and maybe it's going to be in Ethereum, I don't know, it's going to be, I don't know, 2, 3, 4, 5 constellations of rollups, and then this interconstellation communication and transfer value. Maybe it's going to be with a little bit more friction, but probably it's going to happen here. And this is, I would say, what will happen it's my bet in the short run. And maybe in the more long run, who knows, but it's perfectly possible that Ethereum, so the current chain, the Ethereum Layer 1, be converted to a rollup itself. I mean, that would be perfectly possible in the future. But I mean, it's long time for that on there. But this is the way that I see that it will grow is this path. But again, I do not have a crystal ball. What I'm saying is just the feeling that I have and what we are building, and seeing the teams where we are going. Okay, but we need to see.
That's perfect. Thank you for your answer.
Perfect.
I know you have to leave at 7.
I don't even know what time is it. Yeah,
It's
like
3 minutes to 7. I don't know if we have time for one last question.
Yeah.
Okay, Ori, go ahead.
Hey, yeah, just getting on stage. Yeah, thanks, Jordan. I was curious just on one of the last points that you made about like inter L2 or inter constellation or just interchain communication, and how to do that without fragmenting liquidity. And I know there's like a lot of new entrants now with solutions, whether it's like a bridging approach or otherwise, but I'm curious if you're working on, or if you have any favorite contenders for how to unify data, make it really like seamless to move assets and messages across chains, maybe IBC or anything like that. I'm curious if you think those kinds of solutions are relevant for EVM chains.
So for me, the solution goes with for having composability. The end goal is to have fast proofs. So if you are able to build the proof in 10 seconds, then you will have composability of 10 seconds. So for me, the first thing that we need to solve to have real composability between chains is these fast proofs. Okay. The second thing is, so this is, and with this we can achieve composability inside the constellation. Okay, that means that you trust this proof. You don't need to move the funds in layer 1, and you just reassign one place to the other, and this is done with just having fast proof. If we are talking in interconstellations, which is, I think, is the question that you are thinking about, here the problem is that if you want to do it the right way, you can always do kind of optimistic with some collaterals and these things. Okay, but I'm more a ZK, so I don't believe in optimistic things. So I mean, I want things to happen there. So for me, it's a proof. And if you want to do that, then the problem of two constellations is that they have like different provers, and the problem is that they have different governance for updating the provers. So here the problem is that you need a trust between the two constellations, trust between the two governance of the two constellations, to really trust the prover on one another. If you don't trust the prover, I mean, if you are working in a trustless interoperability, then the only way is to do transfers in layer 1. But the good news here is that you can do these transfers in an aggregated manner. I mean, for example, all the transfers, I mean, if you have 100 transfers that goes from 100 users to from rollup 1 to rollup 2, you don't need to send 100 transactions in L1. You can have one single transaction that consolidates, that consolidates one rollup with the other. But you need these consolidation transactions. This can be done really fast because at the end you can do one of these per block, okay, and you can achieve some composability on that. But you need these rollups to be final, so you need finality. I mean, you cannot do that with an optimistic rollup. You cannot wait 1 week for that. But if you are doing ZK, if you are generating these proofs in a fast way, then this composability, I mean, you can do these transfers, and this composability between rollups can go really fast. And I think this is the in my opinion, this is my favorite way to do things, because it's the simple one. You need fast proofs, which is not obvious, but I mean, the proof right now, we are in 100 seconds on that, and in the new system that we're working right now with, we call it VATCOPS, which is variable degree composite proofs. With this, we could reduce the proof. Also, right now, for example, we cannot do a smaller proofs because we don't allow to split a transaction in between different proofs. This is the IBC idea, okay? But if you split the transaction, which is especially possible, then you can think about smaller proofs. And then if you are talking with smaller proofs, then they can go faster, okay? And then having this composability, a smaller composability, then this is good. The other thing to solve is that's very related to that is the finality in layer 1. Okay, this is the other point that's important, but I know that there is some people in the Ethereum Foundation working on that direction too.
Great, thank you.
Perfect.
Amazing. I have many more questions. But I don't think we.
I'll give you the last one.
Okay. I don't know. I don't know if I can. So okay. Yeah. Good. So it is not clear to me when proto-dank sharding happens, 4844. That's coming around the corner, and these data blobs that are going to be the pillar or the cornerstone for data availability for rollups. These data is only going to be kept for a few weeks. I think it's about 2 months, something like that. How are rollups coordinating to maintain this data somewhere else? Or are they? Or what is the solution otherwise?
The idea is that during 2 weeks, this data is going to be available. So that means that anybody can collect this data. And as far as there is one that's honest, then the system is just honest. And there is a lot of factors in a rollup that has a lot of incentive for the rollup to happen. Okay, so with this should be enough to organize. To organize things so that this data is not lost. So this needs to be organized, but I think this is not a big practical. It's not a practical problem. I mean, it's more a theoretical problem, but it's not. Somebody will get it. I mean, I'm gonna get them. So it's like, and if you are worried for that, okay, just collect yourself the data.
That's what I was talking about. Like, how much of a centralization problem? How much do I need to trust you for me to be able to reconstruct this later on? Or am I missing something?
You need to be sure that this data is available. That can happen because you trust somebody that's collecting this data. That can happen because you collect yourself this data, or because you know that there is so many people in the network that has high interest to collect this data that you just rely on that and collect your data. Maybe it's not a valid assumption, but this is the thing. But the data needs to be available for that.
Mm-hmm. I already know that there are some people working on a blob explorer, and we're gonna have this replicated in many places.
It's gonna be blob explorers. I mean, it's gonna be a lot of information. This is like saying, I mean, it's a little bit like saying that. I mean, if a blockchain, if everybody in a Bitcoin stops and deletes this database, Bitcoin disappears. Yeah, but is this gonna happen? Well, theoretically, okay. But as far as there is one person that continues running the network will continue running. But that's a little bit the same. It's not as big because the network is not that big, and there's not that many people that have the incentive yet. But in the mid-RAM, is going to be a lot of people that will have the incentive to have this data.
Gotcha. Well, okay. So fantastic. I would like to thank you so much for all of your time. I think this was an amazing episode. It was a lot conversational, a lot very interesting. We went very deep into some of the steps or the breakthroughs that went on zkEVM, and thank you so much for responding to all our questions, simple mortals.
Thank you very much to you. Thank you very much to you, Paul. Perfect. Okay.
Fantastic. Thank you so much, Jordi.
Bye.
Have an excellent day.